Okay, so I'd like to thank Joel and Tom and everyone for getting me here. So I'll okay. So this work that I'll talk about was done with my student Anjan Roy and my colleague at Raman Research Institute, Sanjeev Savapandit and Anuttam Narayan in UC Santa Cruz. Okay. So part of this work is published out here and part of it is still ongoing. Okay, so this is the outline of the talk. So I am basically talking about tagged particle diffusion in one-dimensional Hamiltonian systems, and I'll so basically I'll consider various Hamiltonian systems, like starting from the simple models like harmonic crystal and just equal mass hard point gas, and then looking at more complicated models. So I'll describe all these models. So it's various Hamiltonian models, and trying to see if there are like any universal features, and basically trying to understand tagged particle diffusion in all these models. So there's some microscopic studies, and then there's some attempt at trying to understand using fluctuating hydrodynamic theory, and I'll then discuss the results. Okay, so what is the basic problem? So there's a so in one dimensions I have a set of particles with positions x1 to xn. So they are described by all their positions and momenta, and so it's confined in a box with hard walls. So the particles can't go beyond this, and so there are n particles and in a box of size L, and I am looking at the middle particle. Okay, so there are equal number of particles on the both side. So I am looking at this middle particle, and so at time 0 it starts at some position xm0, and at time t it's at xmt, and I look at this displacement, and then I consider various so Vt is the velocity of this particle, and I consider various correlation functions. So this is just the mean square deviation of the particle starting from the from its initial position, and I see how it depends on time. So I consider these various correlation functions. Delta x square, this is the mean square deviation of the particle from its initial position, then delta xt times the initial velocity, and the velocity autocorrelation function Vt V0. So so these averages out here are with respect to the initial distribution, which is taken to be thermal. So after that the dynamics is purely Hamiltonian. So in principle, of course, one could also consider stochastic dynamics, in which case this average would be both over initial conditions and the dynamics. Okay, but in our case, mostly we will be considering the case where this distribution is over the initial thermal distribution. So all the positions and momenta are chosen from the Boltzmann canonical distribution, and then I just run my Hamiltonian dynamics and calculate these correlations. Okay, so these three correlations are related. So and I'll call it d of t is basically the derivative of time derivative of this mean square deviation, and it's exactly equal to this integral of the velocity autocorrelation function, and one can show that this is exactly equal to delta xt times V0. Okay, so all these three correlations are equal, but it's I mean, if it's good to look at all of them separately. Okay, so now so what do I mean by diffusion? So if this I mean, if this quantity, if I take an infinite system, so if I take a finite system, then I mean at long times the system, I mean the mean square deviation has to it can't keep increasing. So therefore, I mean the diffusion, I mean this would go to 0 typically. Okay, so but so if I want to define the diffusion constant, I first need to take the infinite size limit and then take time t going to infinite, and then if this d is finite, then I say that the tagged particle motion is diffusive.
What goes to 0 if you don't do something?
If I take a finite system, yes, and then let time go to infinity, yes, then I mean delta x square is bounded, right? So I mean so either it, I mean either it just goes to, it keeps oscillating, or it goes to 0.
Yeah,
it could keep oscillating, right? Yeah, I mean so yeah, or it goes to 0. Okay, so if it goes to a finite constant, then we say the motion is diffusive, and then it would delta x square would go as I mean, so this is what one typically means by diffusive motion, and this is the diffusion constant. If d goes to 0, then we will call it subdiffusion, and if d goes to infinite, we will call it super diffusion.
Is there a reason you chose the middle particle, so you have less?
No, yeah, I could, yeah. I mean, the boundary effects are minimum for the middle particle. Okay, so this I mean problem has been. So let me just give some review of earlier work. So one of the first, I mean.
Tell us what the Hamiltonian is?
So I will consider various Hamiltonians, and I will describe what I mean the Hamiltonian. So let me first review some earlier work on this problem. So I mean one of the first papers is this paper by Jepson in 1966. It's called Dynamic of a simple many body system of hard rods. So these are just hard rods which collide elastically. Okay, so it's just elastic collisions, and that's all. And so equal mass particles move ballistically between elastic collisions, and this you can solve exactly. And so for an infinite system, what you get is that the mean square deviation goes as so it's diffusive motion, and the diffusion constant is exactly given by this. So this is kBT temperature, and this is the mass of the particles and the density of particles. Okay, and the velocity autocorrelation function has this form. So at large times it's negative, and goes to 0 as 1 by t cube. Okay, so this is kind of an integrable model, because like when the particles collide, they basically go through each other. So you can find n constants of motion, and that's the reason you can solve it exactly. The other problem which you can solve exactly is just the harmonic chain. So it's so again in this case, so this is again a paper in 1966 by Mazur and Montrol, and again you find that it's diffusive. So the diffusion constant is in this case is given by kBT by 2 density into the speed of sound, and the velocity autocorrelation function has a very different form. It's sin omega t by t to the power half. Couple harmonic chain.
So again,
you can do it exactly right. Yeah. So this is again in the like you take in n going to infinite limit, and then get this results. Okay. So so this is a sort of different model. It's a stochastic system. So instead of like Hamiltonian dynamics, if one considers like the Brownian particles diffusing, but with the constraint that they can't cross each other, then you get something very different. So in that case, the mean square deviation is actually subdiffusive. It goes as root of t, and so basically in the Hamiltonian case, the individual motion is kind of ballistic, and because of the non-crossing condition, it becomes diffusive. And in this case, it's the single particle motion is diffusive, and because of the non-crossing, it becomes subdiffusive. They can't. This is non-crossing hardcore particles, right? Okay, so this is also something which one knows exact results. Okay, so let me just say that there are experiments where you. Brownian dynamics, right? Yeah. Right. Yeah.
But again, you can solve.
This also you can solve exactly right. Yeah. Okay, so there have been recent experiments where where you just look at colloidal particles which are constrained to move on tracks like this, and people have actually verified this subdiffusive motion. So here the dynamics, intrinsic dynamics is stochastic, and so this is another experiment where basically it says from random walk to single file diffusion. So at short times you see when the particles don't interact with each other, you see that the mean square deviation goes as t, but at large times once they start filling each other, then it goes as t to the power half. Okay, so
go back to let me just ask a question. So when you take the limit as you go to box goes to infinity, you're fixing density of particles.
Right. Yeah.
Right?
Yeah. Yeah. So I mean this is for fixed density of particles. Okay, so some open questions are the following. So the equal mass hard particle gas, which I showed the exact results of Jepson, and the harmonic chain, both are very special systems. Okay, both are integrable models, And so one question is what happens in more realistic models, like where you if you take a generic Hamiltonian which is not integrable, then do you still get diffusion or not? Okay, so you expect that there is more stochasticity in the model, and so it's not clear. I mean, so that's a interesting question. The other question that we wanted to see is what are like if you have a finite size effects, then you expect it to either saturate or do something at large times, and so to basically study those finite size effects. Okay, so I mean. Okay, so here I mean typically you expect that it should saturate to the equilibrium value. This is not always true. I mean sometimes you find it keeps oscillating, and basically we want to understand this like the finite size effects. Okay, and then finally the question is like if we find that generically it is diffusive, then the one question is how do you determine this diffusion constant? I mean, and so is there a prediction from hydrodynamic theory? Okay, and so another sort of interesting point is the relation of this to thermal conduction studies. So if you take integrable models, then what one knows is that if you look at the thermal conductivity, that that it's ballistic, which means that the thermal conductivity increases with system size as L as the system size. Okay. So in fact, so both for the hard particle gas and the harmonic chain, you know that the thermal conductivity becomes infinite. But in both these models, the diffusion constant is kind of finite. Okay, so I mean, so this is also something we want to understand. I mean,
I would ask another question. So, what can you say about the motion of the individual particle? Is it chaotic? In other words, does it have a positive outcome X?
For generic Hamiltonian dynamics, you are saying, like if I take more. I mean, depends on the model, I guess. I mean, right? Yeah.
Certainly not
No.
harmonic,
For this case, of course, it's both are integrable. So in these two cases, definitely not, right? They are both integrable models.
You would expect it, or did you do calculations that show that in the anharmonic case that happens? Or
In the anharmonic, okay. So let me go to the models that I'll talk. I mean. Okay, so I mean, so there have been some earlier work on this problem. So basically, one question is to make the dynamics non-integrable. Then what happens? Okay, so one way you take this hard particle gas to make it gas. If you want to make it non-integrable, one simple way to is to not take all the masses equal, but make the alternate the particles have alternately different masses. Okay, so alternate particles have different masses m1, m2, m1, m2 like that. Okay, so in that case, when there is a collision, it's not just like particles go through each other. There's it's more non-trivial, and it's not an integrable model any longer. Okay, so you can check that it thermalizes very fast, and it's got quite good ergodicity properties. Okay, so in this model, I mean, this question of tagged particle diffusion was studied in 1985 by these people, and what they found is that instead of this 1 by minus 1 by t cube that you find for the equal mass case, in this case, the velocity autocorrelation function has this minus 1 by t to the power delta with delta less than 1. Okay, so this is a numerical simulation result. Okay, now this result is kind of is actually impossible because if you integrate this, then you get a negative infinity. Okay, and so so there's some problem with this result. Then there are sorry. I mean, yeah. So, like I show, it's kind of very hard to. I mean, the simulations are really. I mean, very. I mean, when I show the simulation results, it will become clear why you might see something like this.
How many particles were they doing?
They were doing 800 particles. 800, right? Yeah. Okay. So then there are some studies on Lennard-Jones gases. So this is just nearest neighbor Lennard-Jones interaction. And there again they typically they find it's 1 by t cube. Okay, so this is and then this question of finite size effects has been studied in the equal mass hard particle gas, and some general results have been stated in various papers also by Joel. And but these results are mostly formal, and one can't really see anything explicit, like you can't see plots, for example, of like how the finite size effects appear. Okay. So that's what we wanted to do. Okay, so for stochastic dynamics, I mean, there has been a lot of recent studies, and people have looked at these finite size effects. And so this is what, like, if you look at the mean square deviation as function of time, I mean there is this subdiffusive growth with T to the power half, and then it saturates in some way. And if you look at different sizes, then you find that it takes I mean you get a longer subdiffusive region, and then it saturates to some constant. So this is this is what we want to do for Hamiltonian dynamics. Okay, so so basically what I will talk about is trying to understand finite size effects in the harmonic chain and the equal mass hard particle gas. So in this case, the infinite system results are already known, and we just want to see what are the finite size effects. Okay, and then I will give so this is kind of analytic results, and then I will talk about some simulation results for the FPU chain and the alternate. So this is the Fermi-Pastor-Ulam chain, which is an anharmonic chain and therefore non-integrable, and then the alternate mass hard particle gas and the Lennard-Jones gas. Okay, so so I'll just show you various simulation results and try to compare what you see here and what you see in this integrable models.
Is there a simple way to understand why one might expect 1 over T cubed behavior? Stay with this. 1 over T cubed. How do I see that intuitively if that's actually what goes on?
No,
Do you believe it's actually 1 over T cubed?
no. For the equal mass, it's an exact result.
Yeah, for equal mass, but even in equal mass, how can you easy to explain why?
No,
I don't know.
I don't think.
It's definitely due to small velocity particles. If you have a small velocity cutoff, you don't get it. I mean, it's
What if I
very
have-
slow particles.
I see.
No, I don't think we ever got a real understanding of why exactly 1 over T.
Can take this modulus random velocities plus or minus 1, let's say. Then you will get an exponent.
Yeah, get it.
Okay, well, maybe that's-
It's a really
So
small
this
velocity.
is
Oh, I'll get an
small
exponential.
Yeah, then you get an
So I don't get, so it's all
It's all
small
small
velocity.
velocities. That's a full
Right, yeah.
explanation.
Yeah, no, it's helpful.
Okay, so okay, so let's first start with the harmonic chain. So so this is the Hamiltonian kinetic energy and interparticle quadratic potential, and this is the spring constant. And so here you can one can just do a normal mode analysis. So these are the normal mode frequencies for a chain of particle n. And then to find the mean square deviation, it's just using I mean a very simple analysis. What you find is that the mean square deviation is given exactly by this, okay, and the velocity autocorrelation function is given by this. So now supposing we just numerically plot this as a function of time, okay, then so this then this is what it looks like. Okay, this is for various system sizes, chains of size 9, 17 and 33. Okay, so now what you see is that the mean square deviation as a function of time, it keeps oscillating, okay, even for very small chains. Okay, so here I mean, so remember that the initial conditions are chosen from the Boltzmann the canonical distribution, and so what you notice is that these oscillations just keep happening, and I mean never really goes to I mean, so it doesn't saturate to the expected equilibrium value. Okay, so here this is the same thing with where this axis has been scaled by n, and this also has been scaled by n. Okay, so so where is the diffusive? So like I said, if you take the infinite system size limit, you should get diffusion. So that's this region. Okay, so
What kind of boundary condition are we?
this is hard fixed boundaries, fixed boundary conditions, right? Okay, so so the diffusive region is really this region. Okay, so this is for the biggest system size. You can see it goes on for a longer time. So here delta x square goes as t, and then you start seeing finite size effects. Okay, and finite size effects basically show up at times when like sound waves can like travel across the system. Okay, so so this is the diffusive regime, and then I mean you could expect various things. I mean normally one would have expected that this should saturate, but here it doesn't saturate. You see these oscillations. Okay, okay. So now we'll come to that later why it doesn't saturate. But let's first look at just this diffusive region. Okay. Okay, so if you look at the diffusive region, it basically looks like this. I mean delta x square is a function of time. This is for two different system sizes. The red one is for I think 128 particles, and this is 256 particles. So there is a small ballistic region, and then this diffusive region, and then you see these finite size effects. Okay, and so this one is just a derivative of this. So this is the diffusion constant, and it basically goes to a constant in some oscillatory way. Okay.
And then I follow the first top one, I understand. What are the other ones below here, where did you change them? Sorry, just
This
time derivative.
is just the time derivative of this.
Oh, it's just time derivative of what
Right,
you
yeah.
have above?
Yeah, right, yeah.
Oh, I see that. Okay, that's
And so there are really oscillations out here which show up in the derivative. I mean, and if you take one more derivative, it's just the velocity autocorrelation function, and so this has this form sin omega t by t to the power half. Okay, and this is just the mod of that. Okay, so this like I said, I mean, you can do a simulation, and you know the exact results, and you can check that. I mean, this is a good check of your simulations that they match with the exact results. Okay. So in the so here there are three distinct regimes. There is short time before which is just ballistic, and it goes as t square. And then if you look at the regime where the sound velocity, I mean the sound waves have not reached the boundary, then you can look at the limit. You can set n going to infinity, and then you can convert this to an integral, and that just gives you the diffusion constant. Okay, so you get 2 dt. So you get the diffusion constant. Okay. And then there is this regime where you get this I mean almost near recurrences. Okay. So even though you start from a thermal distribution, when you plot delta x square, you find these near recurrences, and that I mean basically you have to examine this series sort of carefully, and what we show is that actually the recurrences are not exact. I mean the first recurrence, I mean actually scales with system size as n to the power 1/3. So this can be understood by carefully looking at this series. Okay, so these are the results for the harmonic chain. So now let me talk about the equal mass hard particle gas. So the system is a box with hard walls at the end, and I have n particles at the I take odd number of particles, and the system has only kinetic energy, and all particles have equal masses. So the only interaction is just hard particle collisions, and it's like they just go through each other. The velocities just exchange when a collision happens, and when they hit the wall, the velocities are reversed. Okay, so and again the initial distribution is drawn from a canonical ensemble, which means that the positions are chosen uniformly, and so the particles are ordered in some way, and they maintain that order. And the initial velocities are chosen from a Gaussian distribution. Okay, so in this case, basically, if you look at the space-time trajectories of the particles, then it basically looks like a gas of non-interacting particles. Okay, and then what we are interested in this middle particle, which is colored like this. And basically you can you can map this to a gas of non-interacting particles and extract the correlation functions. So if you look at supposing I am interested in the velocity autocorrelation function of this middle particle, then basically what you can see is that if I look at some time like this, at this time the same particle is the middle particle, right? But at some time like this, some other particle has become the middle particle. Okay. So basically when I calculate the velocity autocorrelation function, if I use the non-interacting system, then I mean there are these two situations, and I can calculate the velocity autocorrelation by summing these two possibilities. Okay, so this is the contribution from the case where the same particle continues to be the middle particle, and this is a contribution which comes from some other particle becoming the middle particle at time t. Okay, so let me just say how one computes this correlation. So I have this now I am thinking of the non-interacting gas, and if I want to compute this thing, then I pick one particle at random, and I ask what is the probability that it goes from x0 to some yt at time t. Okay, so this is just the single particle propagator of a particle confined in a box, which one knows, which one can write a formula exactly, and then I multiply this by v0 vt, and then integrate over all possible xy. Okay, so this gives me this correlation function, and similarly I can compute the contribution coming from the case where another particle becomes the middle particle. Okay, so so using this approach, like one can so we can get analytic results for the velocity autocorrelation function. So I won't go into the details, and so I mean the formal expressions that we get are basically I mean directly related to the results that were obtained by Jepsen and also Joel and Sykes and Perkus. And so I just want to say that our approach is actually it's kind of it's very physical and it's much simpler than the earlier approaches, and you can, and then we have analyzed the for expressions and tried to extract the long time behavior, which I will now show. Okay, so this is what the I mean if you just either plot those numerically evaluate those expressions or do a simulation, this is what you will get for the various correlation functions that we are looking at. So this is the mean square deviation as a function of time, again for two different system sizes. So again there is a short time where it's ballistic, and then there is a diffusive regime, and then there is this finite size effect. Okay. So here I mean in the harmonic chain, if you will remember, it was just oscillating forever, right? But here it just goes to the expected equilibrium like a steady state value. Okay. And this scales with system size as n, the saturation value, as you expect for a one dimensional system. So this is just again the derivative of this, and in this case you can see that this goes to a constant, and then you see these finite size effects. The velocity autocorrelation function, so this is the region where there is this 1 by t cube slope, and then after finite size effects appear, then you get this hump. Okay. So these humps can be again understood exactly from the analytic results. I mean I don't have a like physical understanding of why you get these humps, I mean but this is what you get. Okay. So so let's just compare the results of the harmonic chain and the hard particle gas. So both these models are integrable, and both are diffusive at this short time regime where you do not see finite size effects, and the velocity autocorrelation function is very different in the two models. In one case it is in the harmonic chain it is given by this, in the hard particle gas it is this minus 1 by t cube, and then finite size effects are very different. In the hard particle gas at long times the mean square deviation saturates to the expected equilibrium value, while in the harmonic chain it just keeps oscillating. Okay. So even though I mean both are like integrable models. Okay, so now let us go to non-integrable models, and the first model that I will talk about is this alternate mass hard particle gas. So in this case, I mean when there is a collision, I mean the velocity, I mean you have to look at just momentum and energy is conserved, and then this is how the velocities transform. Okay. So in this case, I mean if you look at the trajectories, they kind of get distorted, and so you can't do this mapping of to non-interacting particles, and so there are no exact results, and I will just show you the simulation results. Okay. So okay, so this is what so if you plot the mean square deviation, so the dotted lines here is for the equal mass case, okay, and the solid lines are for the alternate mass case. Okay. And so the alternate masses are 1.5 and 0.5, and this is the temperature. So everything is the, I mean so the mean density is the same as the equal mass case. So in this case what you find is that it seems to be more or less like the equal mass case, but at after system size effects come, then you see these oscillations which you do not see in the equal mass case. So in the unequal mass case you see these oscillations, and then it saturates to the equilibrium value. Okay.
Which color is the, no, is the dotted stuff?
Dotted stuff is the equal mass case.
And what about the different color lines?
Are for two different system sizes. Right, yeah. Okay, so the blue is for a smaller system size, and the red is for the larger system size. And so the saturation value, actually you expect both to be exactly the same, because whether it is alternate mass or equal mass, because the I mean the equilibrium distribution is in space is exactly the same for both the cases. Okay. I mean it is only the velocity distribution which is different for the two systems, but the spatial distribution is the same. So therefore delta x square at t infinity is expected to be exactly the same for both the models. Okay. And that is what you see in the simulations. but the approach to the this equilibrium value is kind of different in these two cases. In one case you see these oscillations, in the other case you don't.
So you probably told us this already, but how does this transition occur as a function of L?
Which transition?
Well, where you start to see the boundary effect.
Right. Yeah. Oh,
I
so
know it's when the bounce happens.
right, when sound waves, I mean, hit the it scales basically with size. Right. Yeah. Right.
You
And
know more or less where that line is.
right. Yeah. It's with L by C. Okay, and you also know the where it saturates, the mean square, that also you know exactly. Okay, so then if you take a derivative of this, then however you see something strange. So the dotted line has kind of saturated, but the solid line is going down actually. Okay, so it seems to be very slowly going down as a function of time. So this is supposed to be the diffusion constant, right? So if if it has a finite diffusion constant, you expect it to saturate. If it goes down, it means it's going to be subdiffusive. Okay. So there's this difference that that I'll discuss again. And if you take another derivative, this is the velocity autocorrelation function. And if I take mod of this, then I can see the power law tails. Okay. So this is the equal mass case. This is 1 by t cube decay. While for the alternate mass case, the decay is completely different. Okay. So it's now 1 by t. Okay, so it's not the precise power I will discuss later, but I'm just showing this 1 by t line, and if you remember, I told I mentioned like one of the earlier studies saw something like 1 by t to the power 1 minus delta, right? So 1 by t is of course very, you can't get 1 by t because that's it would give a diverging conductivity. Okay, so this has to be examined more carefully. Okay, so. Okay, so now let's basically examine this region more carefully. So I'll just blow up this and also look at larger system sizes. Okay, so if you blow up this region, so now we are doing for sizes till 801, and so this is the diffusion constant, and you can clearly see it's going down, right? This is the equal mass case where it saturates, and this is the value that Jepson's exact result gives you. So it just goes to that constant, while for the alternate mass case it just seems to be going down. Okay, and so in this paper we had presented this result, and what we had said is that this seems to fit to this sort of logarithmic decay. So it's a over b plus log t. Okay, so that seems to fit well. It's just a fitting. Without any explanation.
So in that was true, then the diffusion constant would be the actual T infinity diffusion constant
would be zero.
Would be zero.
Right. Yeah.
With the alternating mass case.
Right. So it would be subdiffusive. It would be subdiffusive. So that subdiffusive. So the mean square deviation goes as t by log t. Right. If this was true. Sorry.
I'm dubious about that.
Right. Yeah. No. So it's yeah. So this is what you get from the numerics. Okay. So one of the referees of our paper was Henk Beieren, and what he said was that what he expects from hydrodynamic mode coupling theory is that this curve should actually be something like this. Okay, so d plus 0.39 by 2 t to the power 2.5. Okay, so he has these exact numbers with also, so which means that at very large times it should go to a constant, so it should be diffusive, and the diffusion constant also one knows exactly. Okay, so this is some number 0.2887, which will be somewhere here.
I'm sorry, I'm a little bit confused about the slide. So the one before, put that back on for a minute. Yeah. So at least I thought I was seeing that you did get diffusion here.
But yeah, but it seems to be slowly going down, right? As a function of time, it's just going down. It's not saturating. Right. Yeah. This one is so now I've just increased this. I'm zooming up on this place, and when you do that, you see something like this. Right. It's clearly going down.
Okay. That's a more larger scale.
Right. Yeah. And yeah, the sizes are also now larger. It's 801, and okay. So right. Okay. So.
But your results would be still
Okay, no, so I'll just show. I mean, then okay, so we just published this paper anyway because we said, I mean, this is what we see. We don't see this. I mean, when we tried to fit this, it wasn't. I mean, it didn't fit at all. Okay, so but then we did. I mean, larger simulations, and I'll just show you. So this is still going on actually. So now the size is 4,000 particles, and this blue curve out here or purple. I mean, it's the simulation results. So this is for size 200, this is for 1000, this is 2000, and then this is 4000. Okay, so this was our earlier fit, and now this is the prediction of from Henke, this thing, and it seems, I mean, it could actually go to this fit. Okay, and this is what you expect for the diffusion constant. So it might eventually go. I mean, like it's a very slow. Somehow decay to the, I mean, asymptotic value. Okay. So
It's not contradicting next result.
it's not. It's consistent, right? Yeah. But I mean, it's still not conclusive. And so we are still doing even larger sizes. I mean, just to make sure that I mean, then just looking at the difference and seeing how it
So I guess
scales.
Hank requires that you do infinite volume, there's no confidence.
Right. Yeah.
There's no sort of finite volume version of that.
Yeah. Okay, so one sort of interesting point is that the diffusion constant for the I mean, actually depends is independent of the mass ratio. Okay, and depends only on the average density. Okay, so because this formula, I mean, the speed of sound out that comes here is does not depend on the mass density. Mass ratio, it only depends on the average density. Okay, and so if the equal mass case, and if you take slightly different masses, that's completely different, the diffusion constant. Okay, so the equal mass case would be somewhere here, and I mean, once you make the masses unequal, then it goes down significantly.
So, in these units, what is the equal mass diffusion constant?
The equal mass is this one, 0.39.
Square root of 2 pi.
Right, 1 over square root. So that's somewhere here, and this one is this value.
But the 0.39 divided by e to the 2
So this at large times this goes to 0, right? So it just goes to this constant.
But is the 0.39 coming from ratio of masses?
No. Okay, you are saying where this constant comes. Okay, I mean, I have no idea, and he just gave this number. I mean, like I've tried to.
Ratio of masses doesn't come in.
Ratio, I don't think so, right? Yeah. No, in the D, this definitely doesn't come in. In the prefactor, okay, I can't say. Okay, so so that was the short time behavior, and if you look at the large time behavior again, so this is the equal mass case where it goes to this constant. In the unequal mass case again, it will eventually go to the to this same constant. It has to go to this constant, but again it's a very different approach to this steady state value. Okay, so you see these large oscillations. I mean, both the amplitude of the oscillations and the frequency of the oscillation scales with system size. So here we just scale with n, and this basically comes from the sound modes in the system. Okay, so for the equal mass case, I guess there are no sound modes, so you just get this smooth approach to the equilibrium value, while in the unequal mass case, I mean, you have these sound modes which are oscillating in and so therefore therefore you see these oscillations out here. Okay, so yes, okay, so that's what I've. Okay, so now so that was the, I mean, that's one version of the, I mean, so I discussed the alternate mass case, which corresponds to the non-integral version of the equal mass case, and then I'll discuss this Fermi-Pastor-Ulam chain, which is again a non-integral version of the harmonic chain. Okay, so again I just show this. So you can't. There's no analytics. So you just simulation results. So for the mean square deviation, so you have this ballistic and the diffusive regime, and in this case, if you look at the diffusion constant, so here it saturates again very fast. Okay, and it goes to this constant value, and this constant actually can be determined. It's again the same formula as I showed for the alternate mass case kBt by 2 twice density into speed of sound. And the speed of sound, I mean, so this has been actually given in I mean recent paper of Herbert from just linearized hydrodynamics. You can estimate this.
Is this an exact formula?
This this one.
Yeah.
No, it's not an exact formula. This so it's basically from hydrodynamics. So the sound speed is exact. The sound speed is exact. The diffusion constant is not right. Yeah. So right. Yeah. But you can see, I mean, the fit. I mean, it works. I mean, amazingly. Okay. So the diffusion constant from this theory and what you get from simulations, it just agrees perfectly. Okay. And the velocity autocorrelation function now again looks like the harmonic chain, but actually the decay is exponential. So it's instead of the harmonic chain was a power law decay with an oscillation, and now it's an exponential decay with again these oscillations. Okay, and again the finite size effects are very similar to the alternate mass case, but here so in the alternate mass case, which one?
So in FPU, particles allowed to go through each other?
Yeah, they can cross, right? Yeah.
So but they're labeled, so you always know which one it is. Okay.
Right. Yeah. Okay. So in the alternate mass case, this was the approach to equilibrium. I mean, so notice that this this one is always below this asymptotic value. Okay. Even though it so at long times it will eventually go to this, but it's always goes. I mean, like from below. For the harmonic chain, it kind of goes to the expected. I mean, like equilibrium saturation value, but it kind of goes in a different way. And yeah, so here again you, unlike the harmonic case, you this goes to the expected equilibrium saturation value, which again you can compute just from the equilibrium value. So this again scales with n. Okay, so so now let me just say that I mean we tried to sort of understand this in a sort of simple way. So some of this results for the Fermi-Pascagoulomb chain. So so basically this is just linearized hydrodynamics, and so I mean so the idea is to think of this I mean so we have this nonlinear chain, but now supposing we get rid of the nonlinearity and say that this all that the nonlinearity does is kind of act like a thermal bath. Okay. So it adds some dissipation and noise into in the system, and otherwise it just looks like a linear chain. Okay. So this is just the linear part, and then I add this dissipation and noise, and I add them in a way that it conserves total momentum. Okay. So this is momentum conserving noise, and so both dissipation and momentum conserve the total momentum. Okay. And this noise has to satisfy some fluctuation dissipation theorem. And in this case, it's basically one can show that in Q space, it's basically given by this. Okay. So this will ensure that the system will equilibrate at long times. Okay. Now, given so this is just linear equations, and one can again go to normal modes and find these correlation functions, and so this is what we get for the diffusion constant and the velocity autocorrelation function. And if I take the system size going to infinite limit, then this can be evaluated, and you get this kBt by 2 rho c. Okay, so which is the diffusion constant that I said works in all cases. Okay, so so this is the diffusion constant, and then you can look at this velocity.
This model works very well, right?
Sorry.
This model works quite well.
This model works very well. Okay, so I'll just show you. I mean, if I just take this, if I evaluate this numerically and I compare with the FPU data, I mean, then it looks. I mean, it's very good. Okay, so this is a comparison of the prediction of this damped sound model with the simulation results of the FPU chain for a small size. so actually k is not a fitting parameter. I mean, only the dissipation constant gamma is only a fitting parameter. This, since we know the speed of sound exactly, that we actually put by hand, and so there's only one fitting parameter, gamma.
But you have a fairly small chain, right?
Right. Yeah. No, this works. I mean, even if you, but it even works for a small chain. That's what,
For a
small
chain.
small. Right. Yeah.
Right,
Yeah.
but you're saying
It works. I mean, right. Yeah. Yeah. For bigger. Right. Yeah. Yeah. Okay. So here I have plotted both the this numerical results and the simulation data, and you can see it works really well. Okay. And the velocity autocorrelation function. Okay. So that's something that's still not understood. So from here, of course, you see the exponential.
Also
In the FPU, you see exponential. Right. Yeah. Yeah. Okay, so this is of course just I mean plotting this numerically. Okay, so this is the velocity autocorrelation function. So now I mean this is something which we have been trying to. I mean, if you just do a naive like large time asymptotic, if you take n going to infinity and do some asymptotics, then what you get is this you don't get the oscillations. Okay, so this is something that and this actually also agrees with what comes out from Herbert's predictions from hydrodynamic this fluctuating hydrodynamics theory. Even when you include nonlinearity, you still get this same decay. Okay, so somehow these oscillations which I mean don't appear, and so it's not clear whether I mean somehow these oscillations maybe they die down if you in the at very large times. So that's something that's not yet clear. That it could be that the theory doesn't see them, or it could be that it's actually goes away. Okay, so let me just conclude. So what I talked about is the effect of non-integrable interactions on tact particle diffusion, and so it seems that in Hamiltonian systems, in all cases, tact part. I mean, you do have diffusive motion. I mean, unlike stochastic systems where the tact particle motion is subdiffusive, in this case it's always diffusive, and the diffusion constant is in all cases seems to be accurately given by this quantity. And the speed of sound we actually now know for I mean for any microscopic model. I mean there's this very recent paper of Herbert where it there's a very clear prescription of how to calculate speed of sound in any microscopic one-dimensional model. Okay, so from that. That's rigorous, right? That's rigorous.
Now, the point is, I mean, what you have to assume is basically, you know, the validity of the Euler equations for such a one-dimensional system. So we have to turn to the out to sort of give us a complete. I mean, so this we don't know, right? But I mean, you know, if you
make the hydrodynamic.
if you assume the validity of the Euler equation, then that's of course from there on. I mean, what actually, I'm sorry for the summary, but I mean, just to answer your question, what we actually really nice is what one should prove is the big Robinson bond for these systems. And that's really interesting mathematics. You know, you start with initial propagation, and then you sort of make a bound of how fast this propagation should move. And if you could bound, I mean, it should be actually very close to the CS completed from that zero. So I think there is actually a very nice mathematical problem behind it, and prove the Robinson bond for this one.
I usually know the Robinson for farm systems.
Well, for there you do it for certainly for non-integrable quantities. You only Robinson bond, and then I think there should be something related also for that.
But if I have a wave equation, then the Robinson should go.
Well, it's a linear wave equation, yes, I mean, but you know, here's a nonlinear wave equation, so it's discrete nonlinear wave equation.
It's discrete, it makes it hard or not?
I think it makes it easier actually, because you know, so
Yeah, I'll have to find out what this is.
No, but I mean, the Robinson bond would be, you know, that's really what should be proven. You know, precise constant, I mean, of course, it's nice for the simulations.
Right. Okay. So. Okay, so some other differences for the alternate mass case, like I showed, the approach to the asymptotic behavior for the diffusion constant seems to be really slow, I mean on the for the FPU case I showed you get the I mean expected diffusion constant I mean really fast, but somehow for the alternate mask case, even though it is known that the alternate mask case has much better ergodicity properties, I mean for this particular quantity, I mean somehow it takes to see the asymptotic behavior seems much harder. And then what I said is that the velocity autocorrelation function can have a completely like wide range of asymptotic behavior. So there are power laws decay and oscillatory decay and exponential decay depending on various models, and the approach to equilibration and finite size effects are also very different in in the different models. And for the harmonic chain, I mean this is sort of some sort of very funny thing. You don't see equilibration, and there are this very near I mean near recurrences. Okay, so thanks.